Welcome back, guys, to the second part of Chapter 5 here. The lecture on Chapter 5, we ended up last time talking about concentrations, what a concentration is, what molarity is. We talked about how we can calculate molarity. We talked about how we can dilute solutions. And we ended up I introduced saying, hey, we can do stoichiometric calculations using concentrations as opposed to just grams. Like what we talked about, we can do the same calculations we covered in Chapter 4 with limiting reagents, theoretical yields, and percent yields with concentrations. And so we're just going to look at a couple different calculations we can do with concentrations in a stoichiometric way. And then we're going to start talking about electrolytes and non-electrolytes to kind of prepare ourselves for probably what will be part 3, maybe depending on how quick this goes, depending on different types of equations and chemical reactions and looking at those. And so let's go ahead and let's go over to the board. So I have a question that's already on the board. And what I want us to do is to think about how many what's the molarity, right? I want to know what the concentration is of calcium ions. Let me go ahead and do this just to be precise, right? I want to know how many calcium ions are in 0.025 molar calcium nitrate, right? And so there's a couple assumptions that we're going to make, and especially after we talk in a little bit about different ionic compounds, is we're going to assume that everything dissolves, right? Everything dissociates. And so what happens is when we put an ionic compound into a solution, we'll talk about this in the next slide, but I'm just going to go ahead and introduce it here. When we put an ionic compound like calcium nitrate in the solution, it does not look like this, the way we write it on the board. What it looks like is, so let's say we have a beaker here with water, we put our calcium nitrate in, it actually looks like this. Right, that those ions separate, right? It's called dissociation. They dissociate. We'll talk about acids and how acids do the same thing. And so we want to know, in this example, what's the molarity of calcium 2+ in this. We also want to know how many ions, right? And what are the of the ions of this? And so let's go ahead and look at it real quick. So the molarity of calcium, +2. So let's say it dissociates completely like we said over here. What is the molarity of the calcium? Exactly, it's going to be the molarity of whatever the compound is, right? Because for every 1 mole of calcium nitrate, there is equal to 1 mole of calcium ions. So now let me ask you this. Let's say so this is for calcium. Let's look for nitrate. What's the molarity of the nitrate? So for every 1 mole, let's look at the ratio of calcium nitrate. It's going to equal 2 moles of nitrate because of that little 2 there. And so what we'll do is we'll take 0.025 to multiply it by 2, and we get 0.050 molar, right? And so this is, again, we talked about molar ratios. We talked about ratios both within a compound. And so one of the things that we need to keep in mind is this ratio. These ratios are very, very, very important. So let's go ahead and do another question. So I want to know in liters, right? So we're looking for something that's in liters. So in liters, what is the volume, what in volume, right? Liters is volume of, we're going to take 0.1 molar potassium chloride, and we're going to react it with 0.150 liters of 0.175 molar lead nitrate. So I don't know if you guys can see that. So what we're going to do is we're going to do a reaction like what we did in lab and what we're going to be doing in lab, where we're taking this 0.150 molar potassium chloride, so KCl, and we're going to react it with 0.150 liters of 0.175 molar lead nitrate. And I want you guys to tell me in liters how much would it take to completely react with this. And so here's another way that we can do, and this will come back again when we talk about acids and bases in a slightly modified form, and this is known as a titration, right? How much of one substance does it take to completely react with another substance? Oh, but where do we even start with this? Oh, that's right. You guys are right. We need an equation. Again, we need an equation to make sure we can understand what is going on. So I'm going to erase that from, right? Because we need to know the mole ratios. And all of these are going to be aqueous because they're in water. Okay, so we can solve it now, right? You're right. We need to balance it. So go ahead and take a minute and just to practice balancing it. These are pretty simple to balance. So we're going to do there. We're going to do there. Perfect. So now we have a balanced equation. We know the molar ratio. So now let's think about how we're going to solve what is the volume in liters of this much KCl going to react with this much lead nitrate. So what do you think we have to find first? Exactly. We have to find the moles of this that we're going to be reacting with. So remember, we have a volume in liters and we have a molarity. And so all we have to do is take 0.150 liters, multiply it by 0.175 moles per 1 liter, right? Because that's molarity. Now, what I'm going to go ahead and do is I'm going to keep the train running, right? You can solve it here, find the moles of here, and then just add another step. You can just keep it going, whatever's easier for you. And so we know from the equation that 1 mole, I'm just going to put PB for this, is going to react with 2 moles of KCl, right? Just by looking at the equation, 1 mole of this will react with 2 moles of this, just like we did with our limiting reagents. 1 mole of lead nitrate will lead to 2 moles of potassium nitrate, or 2 moles of potassium chloride will lead to 1 mole of of lead chloride. And so then what we can do, so we know we have 2 moles of KCl. Well, we know we have a molarity right here. So if we're going from liters to moles, using molarity, we multiply. If we're going from moles to liters, we're going to divide. So 0.150 moles of KCl for every 1 liter, right, is in 1 liter. When we calculate all of that, we get 0.350 liters of potassium chloride. Right? And so again, it's a very similar process. We have to find the moles, We use a molar ratio from a balanced equation, and then we can either find how much of a product we're making, or in this case, how much of a reactant that we need to completely react, right? For that reaction to go to what's known as completion. And so let's go ahead and switch this. All right, so that's stoichiometry, right? So it's very similar things to what we've seen before. Now let's talk about a little bit more about solutes in the solution. Okay, the solutes, there's two different types. There's electrolytes and there's non-electrolytes. If you have ever drank or paid lots of money to drink Gatorade, you know all about electrolytes, right? Electrolytes are dissolve in water, and what they do is they conduct electricity. All ionic compounds, if they dissolve in water, are electrolytes because they're charged. Those that completely dissolve are strong electrolytes. So things like table salts, right? If you put table salt in water and you stir it around, it will dissolve completely. That is a strong electrolyte. There are some electrolytes that aren't strong electrolytes, and they won't completely dissolve, and we'll talk about those in a minute. Then there are non-electrolytes. Non-electrolytes dissolve in water, but do not conduct electricity. Things like sugar. If you were to dissolve sugar in water, and then you try to complete a circuit with it, it won't work, as you can see in the little picture there at the bottom of the presentation. And so, you know, these are electrolytes and non-electrolytes. That's just the term that we're going to use, and they can be strong or weak. Well, acids, as we're going to see, are electrolytes to an extent. Some are weak electrolytes, right? So they're usually weak electrolytes. Let me say that. Some acids are a little bit on the stronger end, some are weaker, but they're still electrolytes, right? Because again, an acid is a hydrogen molecule plus usually a negatively charged nonmetal. So like hydrochloric acid is HCl, hydrofluoric acid is HF. You have acetic acid, which is the picture with the black balls on the right there. It's a weak acid, and what we mean by weak acid is it does not completely ionize in water, right? We use vinegar, which is acetic acid, in our cooking. We can use it because it's a weak acid. We do not use hydrochloric acid in our cooking because it is a strong acid and it completely ionizes into solution, and that's where the problem comes in. And so we need to know kind of basically what is a weak acid and what is a strong acid. Where we can find that is in table, let me just double check it, in the 5th edition. I know it was table 4.2 in the 4th edition, but like I said, since they switched and they separated, let me just make sure. It's table 5.2. That it was just a simple 4 to 5. So table 5.2 gives you some examples of strong acids. And what do we mean by strong acids are those that completely dissociate in water into a hydrogen and whatever it's else. So in hydrochloric acid, you have a hydrogen ion and you have a chlorine ion or chloride ion. And then there's also strong bases as well. And we'll talk a little bit about acids and bases when we actually get to reactions of those two. Right now, we're just talking about what is strong, completely dissociates, and what is weak, doesn't dissociate as much. Now, some ionic compounds, as we said, are not soluble in water, right? Not all ionic compounds dissolve in water. If they are soluble, they dissolve. If they're not soluble, they don't dissolve. And usually what they'll do is they precipitate out. In a lab, right, we might see a reaction where a precipitate is formed. That is the solid that forms in the reaction. There are solubility rules about different ionic compounds. And you can see it here on this table 4.1. Again, it's table 5.1 on your guys' book. If you have the 5th edition, this table will be given to you on an exam. I'm such a nice guy, I know. But this table will be given to you on an exam